Good day and welcome back to our fifth and final installment on limit laws. I want to take this chance to remind you of something I will continue doing throughout the semester, is that we have a list of suggested problems located on Canvas that are for problems in the textbook, mainly odd ones where you can look up the answers in the back. I highly encourage you all to spend time looking through the textbook, working those suggested problems as additional examples, and really focus on understanding what is going on. That is to say, don't be hyper focused on matching a single solution in the back of the textbook, but do you understand what's going on? Are you properly showing your work? And as you progress through these, don't hesitate to stop by office hours or drop me an email with questions. In this video, our main topic to get started is going to be what we might think of as a last limit law, at least for the moment, something called the squeeze theorem. And what the squeeze theorem tells us is something kind of very intuitive. I'll draw a picture to go along with this. But if you have three functions, f of x, g of x, and h of x, that satisfy these inequalities, and the limit as x approaches a of the smaller function is equal to the limit as x approaches a of the bigger function. Well, if the smaller and the bigger function are approaching that same number L, if something is squeezed, or you might say sandwiched between them, the only possibility is that middle function also has to approach L. So the conclusion is then the limit as x approaches a of g of x is also equal to L. And let me go ahead and just draw a picture representing this. And if the words didn't convince you, hopefully this illustration will. So we have these three functions. We have this smaller function f, and I'm just going to draw kind of very, arbitrary representations of a function f. And graphically we can see it looks like the limit as we approach a is L. For an input close to a, those outputs appear, close to L. And note, as I've told you and I will tell you, the pictures don't have to be perfect. Just kind of get that point across. And then we have this larger function, h, which also has that limit of L as you approach a. And then we're saying g of x is anything squeezed in between. And now when I draw in this function h of x, it could be g of x, it could be anything in between. So I'm just going to kind of draw something in, but no matter what, if it's squeezed in between, when you get close to a for your inputs, those outputs, if it's squeezed between f and g, must also be close to a. Now, the difficulty that we encounter many times when we're applying the squeeze theorem is we really need these inequalities as a starting point. As we will see in our next example, what we will typically have is this function g whose limit we want to evaluate. And somehow we're going to have to come up with these inequalities, that is, find this smaller and larger function that have the same limit. But luckily for us, when we apply the squeeze theorem, it's going to fall into typically one of two scenarios. We give you an inequality to start with, kind of a hint to use the squeeze theorem, which I will refer to as ST, or it has the form that we see below. So this is a very common example that involves the squeeze theorem. And note, the wording of the problem is generous. I'm telling you to use the squeeze theorem, ST, but instead I simply could have had the wording be evaluate this limit, and because of your extensive practice, note my optimism, you would know to use the squeeze theorem. So what we need to do is somehow build up that desired inequality where we're thinking of the function we are taking the limit of as being kind of our g of x. So we need to come up with something smaller and larger that have the same limit as we approach 0. And let me just note immediately before doing anything else, we can't just substitute in 0 because 2 over 0 is an undefined quantity. But what we can do is we can utilize the fact that we know something about how small and how big a cosine can be. So hopefully that is something you recall from your extensive trigonometric experience. If you look at cosine of anything, I'm going to leave it blank for the moment. It does not matter what the input is. As long as you are defined, the biggest a cosine can ever be is 1. The smallest it can ever be is -1. And as long as we stay away from 0, and remember when we take a limit as x approaches 0, it does not matter what happens at 0. So we know -1 is always less than or equal to this cosine, always less than or equal to 1. Well, we also know that x to the 4th is positive. So if we multiply through by x to the 4th, we keep the equalities in the same exact direction. So this is because x to the 4th is always bigger than or equal to 0. And note, now things are looking really good. We can take the limit of the smaller function as x approaches 0 and the larger function as x approaches 0. They are both polynomials, so what we can note is we can use the substitution property. So since the limit as x approaches 0 of minus x to the 4th equals 0, and I'm going to justify that with an SP, and the limit as x approaches 0 of the larger function x to the 4th is also 0, which we'll justify with the SP. What we know is by the squeeze theorem, and we should justify, tell your reader, what property you're using. The squeeze theorem, we know the limit of the larger function is 0, the limit of the smaller function is 0, so the only possibility is that function squeezed in between, the red curve g of x that we see above, is also going to have a limit of 0. And the common question that I know I get here is, maybe first of all, how would I come up with this? And the answer is, well, once we've seen the idea and how we can really, utilize this common fact related to trig functions, cosines and sines, it becomes much easier for us to recreate in the future. A second question is, how much of this work do I really have to show? And my answer is, well, all of it. The only thing I think you could get away from is if you didn't write because x to the 4th is greater than or equal to 0, you would be okay. But everything else really needs to be included. That is to say, you have to justify where this inequality comes from with a starting point, claim and show what the limit of the smaller and upper function are with proper justification, tell me you're using the squeeze theorem, and write down that conclusion. And for now, just note when we see functions again having kind of this form, we should think of, attempting to apply the squeeze theorem if it's appropriate. So we're now at the point where if we were meeting in person, I would once again be turning the floor over to you. You can find in Canvas a class worksheet associated with limit laws. And what I would typically do kind of in person during a semester when we were meeting is I would have you form groups of 3 to 4 students. I would pass out the worksheets. I would give you some time to work on them, and then we would probably discuss one of the problems as a group or as a class. And then what I also will do is post full solutions on Canvas. And I just consider these worksheets to be good additional practice problems where you can work through them on your own and then check versus those solutions. And not only will the solutions tell you the answer, but they will show you kind of how I would work through the problems, how I would organize my work, how I would present them. And remember, if I've done something one way, I certainly cannot fault you or typically deduct points for you doing it the same way as well. So it's really good practice for multiple reasons. So what I would suggest that you do is you pause the video now, go to Canvas, open up that class worksheet. It only has 4 limits on it, and take roughly, I'd give you probably 20 to 25 minutes in class to work through it. So pause your video, see what you can do, and then come back and I will go over one of those problems to give you some additional intuition, but the full kind of written or typeset solutions can be found on Canvas. So hopefully you've taken some time, you've found that class worksheet for limit laws on Canvas, and you've worked through as much as you could in, say, a 20-25 minute period of time. What I'm going to do now is go over, I've chosen problem number 3, where you're asked to evaluate the limit as t approaches 9 of 9 minus t over 3 minus the square root of t. And in order to evaluate this limit, our first thought or bit of intuition is, just see what happens when I plug in 9. And I can't just simply plug in 9 because you end up dividing by 0. So you're in this position where you need to do some type of algebraic manipulation. But note what's causing the trouble, this 3 minus square root t. We could maybe make this a bit easier to work with. What we are going to do is multiply by the conjugate over the conjugate. So we're going to think in this case that our a value is 3, our b value is square root of t, and remember the conjugate of a minus b, which we have as our denominator, would be a plus b, and the reason that this becomes nice algebraically is it's a difference of squares. So it's kind of the reminder. So I'm going to multiply this by 3 plus square root of t over 3 plus square root of t. So we haven't changed anything. We've simply multiplied by 1 and it fades away. So we have the limit as t approaches 9. Note, in the denominator we have a difference of squares. So that would be a squared minus the square root of t squared. And so this works out very nicely with the square root portion, because when you square it, that troublesome square root disappears. And in the top note, we have 9 minus t times 3 plus the square root of t. And this looks awfully good because immediately now, upon the algebraic technique of multiplying by the conjugate over the conjugate, this simplifies drastically. So sometimes you have to complicate the situation in order to be able to simplify it. So we are left with the limit as t approaches 9 of 3 plus square root of t. And note, when it comes to evaluating this limit, we cannot simply substitute in 0. That might give you the correct answer, but it's not something that's justified. The reason being is this is not a polynomial, it's not a rational function, we cannot use the substitution property, but what we can do is go ahead and use our limit laws. So there needs to be some type of intermediate step. Our limit laws tells us we can take the limit of the first plus the limit of the second. And the limit as t approaches 9 of any constant is that constant. And now, because it's the limit of a square root, we need to use one more limit law and think about taking that limit and pushing it inside the square root. So we end up with 3 plus the square root of 9, which is 3 plus 3, and we have 6. And I know I sound like a broken record. It's somewhat intentional, but make sure you're using good mathematical notation. Make sure you're properly justifying your work, i.e., using your limit laws. And the reason I keep reminding you of this is for multiple reasons. One, I know that I've had many students who are frustrated when they get points off for not doing so. And now I can point back and say, I've told you a whole bunch of times. And then secondly, as we get into more involved, more difficult problems throughout the semester, it's very important to use that proper mathematical notation so that we do not make silly mistakes. And it also gives us a nice, coherent, logical argument that one can follow. The notation is to mathematics what punctuation is to an English course. So that finishes up our discussion on limit laws, but there's plenty more to come. So stay tuned and take care.